We're looking at the source code to Monero, the secure, private, untraceable cryptocurrency. This is Answer Everywhere, and we look at source code. We are doing 30 minutes time boxed, and so we will set a timer for 30 minutes and just see what we can find in the Monero repo within those 30 minutes. I don't really know anything about Monero. I'm sure they have a nice white paper and they describe their cryptography. I'm pretty sure they try to be ASIC resistant so that you can mine it on your CPU. And I know that they're focused on privacy and being less traceable than Bitcoin. Bitcoin, of course, writes all of the transactions publicly onto a ledger. And so you can do forensics on those transactions. I'm sure if you have like whatever 10 grand, you can probably get some Bitcoin forensics tools. None of these looks really promising, but I'm sure they're out there for people who do like forensic accounting. And I don't know really what we expect to see. It should probably look like, I mean, the code probably looks a lot like Ethereum and a lot like Bitcoin. There will be, it's a blockchain, I believe at least. I might be surprised. There will be opcodes and crypto. This is written in C++ with some C and some Python. I'm guessing Python is mainly for like build or possibly testing, like development script sort of thing. I'm guessing C++, well, I don't have to guess, it's 81.7%. It's the bulk of everything. And then my guess would be that C is there for maybe efficiency in a few areas, or possibly as part of the ASIC resistance. It looks like probably everything is in source. We have crypto note basic, the daemon, the daemonizer, which I guess makes you into a daemon. Hard forks. How do we have multiple hard forks? I don't know. LMDB, some kind of DB, LM, I don't know. Mnemonics, that might be for cryptocurrencies often use mnemonics for like password recovery. Device Trezor. So these are, I don't know. Trezor is like a hardware based wallet, which is essentially like a combination of like a YubiKey kind of chip, I think, with some ability to have a crypto counter and like a screen so that you can see stuff. RPC should be the RPC implementation. Wallet is probably just kind of like nice functionality for implementing the wallet. All of the other stuff like the blocks and crypto and stuff that go into the wallet are in separate directories. RPC is, I think maybe I just said is the RPC implementation. P2P should be mainly about communicating and discovering peers. Ringkut, I don't know. Serif is crypto. This may be an extension or something. Serialization. We saw some serialization stuff in the Go Ethereum. Multisig should be multi signatures. So like maybe like 2 out of 5 people have to sign something or something along those lines. So I'm not sure. I'm not sure where the real what I would like to do is see the things that make Monero different from Ethereum and Bitcoin, since those are the 2 cryptocurrencies we've already looked at. But I don't know yet where that is. But we'll take a look at hardforks.h. And what I'm looking for here is like, is there any like magic numbers? Like in the Ethereum stuff, we saw that there were like they had listed specific accounts that were going to be handled in a hard-coded way because of a fork. And this is just has some methods. A hard fork type has a version, a height, a threshold, and a time. So this is maybe just for keeping track of hard forks. I don't know how often there are hard forks. And we do have a list of hard forks. Okay. So these are like hard-coded hard fork information. Let's look up hard fork Monero. Monero will undergo a network upgrade. So Monero hard fork, 4 new coins, and what you need to know. And then I guess when Monero, maybe when they introduce new things, they do a hard fork and they keep track of it. Maybe that's what's going on. For example, enhanced privacy features with hard fork. Privacy coin Monero has developed a non-contentious hard fork to boost its privacy and security feature set. A non-contentious hard fork. I don't know how you define as non-contentious, but this is like, to me, the hard fork thing is a problem if the idea is that like the code is the truth, then the ability to do a hard fork is like a way to socially override the truth. And I understand why that's tempting, but I feel like that that maybe undermines the overall premise. So here's LMDB, some kind of database. I don't know what kind. LM. There's some LMDB handle. Maybe LMDB is an existing thing. There's IMDB, Lightning Memory Map Database. Is it? It's an embedded transactional database in the form of a key value store. This looks like it. As part of OpenLDAP. They took a database from OpenLDAP. It is not a relational database. It is strictly a key value store, like BerkeleyDB and DBM. So I'll ask, I guess, ChatGPT. So tell me about how to choose between LMDB and LevelDB. You're just going to hang? Let's ask Gemini. Okay. So LMDB is extremely fast for read-heavy workloads. Due to memory mapped file I/O, write performance is very efficient. Concurrency allows multiple read transactions to occur simultaneously. Only one write transaction can occur. It's fully ACID compliant, etc., etc. LevelDB has good read performance and very fast write performance for write-heavy workloads. If your application is read-heavy and requires consistent high-speed reads, LMDB is a better choice. Oh, okay. Well then. So I guess we're probably read-heavy, or they chose the wrong database, or ChatGPT is wrong. All other things are possible, but I'm guessing that they know what they're doing. Mnemonics, or what, in English? So these, I think, are the mnemonic words. Let's see if we can find out anything. I guess this is just some like vector or whatever that we index into. And then there's one for every language that we support, like Russian. I don't know what this is. Lojban. We have singleton and language base and electrum words. Mnemonic seed generation and wallet restoration from them. This file and its CPP file are for translating Electrum-style word lists into their equivalent byte representations for cross-compatibility with that method of backing up one's wallet keys. Okay, so that's what this is. This is the mnemonic words for encoding a key as a list of words, and so in theory, you can remember the words better. I don't know what Lojban is. New Lojban word list. Huh. What language is this? I mean, maybe that's the name of the language, but where is it spoken? Lojban. Lojban is a logical constructed human language created by the Logical Language Group, which aims to be syntactically unambiguous. So it's kind of like Esperanto. Huh. Okay. Some intentionally constructed language. I don't know who speaks it or or why that's one of the things they implemented. I don't know if they implemented Esperanto, but I closed the directory, so we'll see. I didn't open a blockchain database or blocks, but I probably should. And I don't think I opened Common. So let's open some of those. Okay, here's Wallet. We have a message store. I guess we're storing messages. A ring DB. And the ring DB takes a file name and the Genesis block. You can add rings, remove rings. You can blackball a worker. Let's look up ring DB Monero. This may be something about ring like signatures or ring signatures, what they are, and do they ensure privacy in Monero? What are ring signatures? A ring signature is a privacy-enhancing cryptographic digital signature used to protect any information on signatures made by Monero users when they want to make any transaction. That's basically just fluff. Here we go, ring signature. In cryptography, a ring signature is a type of digital signature that can be performed by any member of a set of users that each have keys. So the setup is that we have a group of users, a set, if you will, and it can be performed by any member of the set. So I guess it's like a one of n signature, multi-signature thing. Anyone who has the keys, it sounds like, can perform the signature. Therefore, a message signed with a ring signature is endorsed by someone in a particular set of people. One of the security properties of a ring signature is that it should be computationally infeasible to determine which of the set's members' keys was used to produce the signature. The set's members' keys. I am going to interpret this to mean that the main thing that's infeasible to determine is which person signed the thing. And I guess this is kind of like an anonymity set. And I don't know how large the Monero rings are, but I suppose the idea is that if we take it out to the limit, perhaps the set is the entire group of Monero users, and so nobody can tell who sent which transaction. Ring signatures are similar to group signatures, but differ in two key ways. First, there is no way to revoke the anonymity of an individual signature. And second, any set of users can be used as a signing set without additional setup. Here's some implementation. And so how does Monero fit in? All right. A ring signature makes use of your account keys and number of public keys pulled from the blockchain. In a ring of possible signers, all ring members are equal and valid. There's no way an outsider, blah, blah, blah. But how large is the ring? I'll ask the AI. So Monero uses ring signatures to hide signers. How large is the set of members who can sign a given signature? It's called the ring size is currently fixed at 11. Previously, users could choose the ring size, but for consistency and transaction efficiency, it was set to 11 in the Beryllium Bullet release. The additional members of the ring signature are called decoys, and their public keys are pulled from the blockchain. Okay, so I guess these are pulled relatively randomly. Are the keys of the decoys pulled randomly? They're not pulled randomly. They are chosen from past transaction outputs on the Monero blockchain. The triangular distribution is used to choose which of the decoys. This method ensures a good mix of old and new outputs while maintaining efficiency. Okay, the triangular distribution. So maybe there are a few, I think, common triangular like probability distributions. I'm guessing it's one of those, like beta or something. Let's look that up. Triangular. The triangular distribution is a continuous probability distribution. Oh, okay. So this is like a hard triangle. Blah blah blah. Yeah. Okay. So it's its own distribution. Fine. I'm not sure if that's literally what they use. Maybe we can look up triangle. Triangle. So we get other. We have triangulo. About triangle. And what's it called? Decoy. Let's look at the decoy stuff. So here's rict sigs. I guess ring CT. I don't know what CT is. But so we have decoy indices. This code is unreadably short variable names. So sig.s is going to be set to key v of n. What is n? I have no idea. Probably key v is some like the value for key n. We're creating a C new. What is C? No idea. What is L? R? I have no idea. And we get this pre-comp. I guess they don't like to name things. And then we have some while loop. And skgen is maybe, I don't know, we're setting sig.s to it. So maybe it's the thing that's generating the signature. And we have this sc mult, and we have some pre-computing points. Points of what? I'm not even sure what kind of crypto we're using. Probably some sort of elliptic curve. Verify Borromean. Let's see if we can find what it's including. We're including rict sigs.h, bulletproofs. I think bulletproof signatures is some part of the Monero thing that I've heard of. Okay, so this is bulletproofs. Maybe bulletproof is the type of proof. Bulletproof proof. Let's look that up. Monero bulletproof. So we're seeing some of where they do their crypto stuff, but I'm not, not knowing enough about Monero. We're not going to really understand it with really 11 minutes left to go. Ring CT. We'll look up ring CT. Was introduced to obfuscate transaction amounts. One goal of ring CT was to prove the sum of inputs dash outputs in the transaction was equal to 0. Okay, so to prove that the output should be, I guess, negative numbers, the inputs are positive numbers, and when you sum over all of them, you should get 0. So you're spending, each transaction spends as much as it inputs, and all outputs were positive numbers. Okay, so I got the convention wrong. Oh, maybe this is literally inputs minus outputs. Okay, so scratch what I just said. The convention is that these are both positive numbers, and you're just taking the subtraction. And why is that something you can sum? I'm not sure, but I guess there are multiple inputs and multiple outputs, and you can sum them, and you should get 0. The whole transaction is you're taking in you're sending out as much as you're taking in. Hello. So bulletproof is like a ZK, like a zero knowledge verification scheme. Okay. I used it while working on ZK stars. Cool. All right, interesting. So to accomplish this, 2 kind of ring signatures were constructed. 1 ring signature for the whole transaction to prove that the sum is 0, and a set of ring signatures for the subset of transaction bits to prove the outputs are positive numbers. Okay, so they're trying to, they have 2 conditions on this computation, and they I guess used to sign them separately, and this led to a large thing where it comes to bulletproofs. The Stanford Applied Crypto Group wrote a paper presenting a new kind of range of proofs called bulletproofs. They are short and non-interactive. Zero-knowledge proofs that require no trusted setup. So they're short. That's good. I really meant to open this paper. I'll read this paper later. 46 pages. How much of that is appendix? Most of it. It seems to be a theme in CS papers, but I'll read it anyway. Okay, so this is some zero-knowledge proof that has like a shortness property. Borromean, I don't know what Borromean signatures are. Short signatures I've heard of. I don't remember the details of them. But we'll look them up and a Borromean link. The Borromean link, I guess, is it the same as the Olympic? There's like 3 interlinked curves. Okay, so it's some kind of link, and I guess there's some, at least metaphorically, some the signature scheme it has some topologically similar properties, perhaps. Schnorr, I think, is classic, no? Okay, so it was patented, but the patent expired in 2010. When was it made, though? Schnorr. Klaus Schnorr. His picture is in black and white. He received his PhD in 1966, and he's 80 years old. This Wikipedia article is telling me that he held his patent until 2008, but maybe he sold it or something. All right, and so this is some signature thing. It's known for its simplicity, among the first whose security is based on the intractability of certain discrete logarithm problems. Okay. So unlike ECC signatures, Schnorr offers linear signature schemes. Okay. Yeah, okay. So we can aggregate signatures, sure. So I guess you can sign over linear over what? I'm guessing linear over like the concatenation of messages. Okay, so elliptic curves have the multiplicative property. So if you have two scalars x, y with corresponding points big X and big Y, the following holds. I don't know what this notation is. I'm guessing maybe G is like a signature. So if you take X and Y, whatever G on the outside is, it's equal to doing them separately, which is equal to X plus Y. Schnorr signatures are of the form S equals R plus E dot K dot. This construction is linear too, since it fits nicely with the linearity of elliptic curve math. What? I just don't know what this notation is. But I'm going to guess G is a group generator. So we're just doing multiplication. Okay. Or maybe it's supposed to be a coset. I don't know. I just don't know what that notation is. So let me ask the Gemini. So what does it mean for Schnorr signatures to be linear? Linear over what? A unique property. We're adding two valid signatures. What does it mean to add? For the same message, for the same message results in a valid signature for the sum of the corresponding public keys. Now imagine two parties, Alice and Bob, both sign the same message. We can add their individual Schnorr signatures, which consist of two values each. The resulting signature creates a new one. The new signature, when verified with the combined public key, will be valid for the original message. So not over concatenation, the message remains the same. And the linearity is over I don't know if you would say it's like the message is fixed. So the message defines some sort of like space or whatever. And it's like linear over the keys in some sense, I suppose. It's a double-edged sword. While it enables cool features, it requires careful implementation to avoid potential security vulnerabilities. So if Y is a private key, then YG is a public key. Okay. G is multiplied to make it computationally infeasible to get back. Okay. So Y is the private key, and then we multiply by the group generator to get the public key, is what this notation is. I think I closed the tab, but that's super useful. Thank you, compilation exe. Are you a crypto person, compilation exe? This is extremely useful. All right, so we never found out what bulletproof proofs were, but we only have 4 minutes left, and it's seems to be an advance on the signatures they were using before. Actually, we did find out what it was. It was the Stanford had some way of doing shorter proofs, like a zero knowledge proof type of thing. Here's gen multisig. Something about multisig, maybe generating stuff. Generates a set of multisig wallets. Okay, so this is going to generate a multisig wallet, which I think is basically a wallet that has maybe one root key, maybe a couple of root keys, but then is able to using something like a key derivation function, generate other keys. Here's common. Common is a bunch of stuff like DNS utils, download.h, presumably for some sort of fetching, notify, pod class. I don't know what pod class is. Pruning, timings, updates. That's these almost look like utilities. Here's blocks. We're not going to be able to understand much about the block structure with the time we have. I'm curious what we see things like mainnet, stagenet, and testnet, which we haven't really talked about, but there's basically Bitcoin has them too. They're just like how if you have a deployment for your app, you might have a production deployment and a testing deployment. So that like when you're developing like some Bitcoin application and you have a test that needs to send some Bitcoin and you want to verify it goes through, you don't have to spend real money to do that. And similarly for Monero and Ethereum. Here's net. It all looks, so we've got Tor. So maybe this is just like built-in support for networking over Tor, which is cool. ZMQ, I'm not sure what that is. ZMQ. Zero something. Zero MQ, maybe? Yeah, probably. Asynchronous messaging. Here's multisig. We're going to ignore this. Serialization. We'll ignore it. I at least want to see some of the opcodes just to verify that it's something similar to what we've seen before. We have a kryptonite R JIT. So we have some sort of just-in-time compilation for something crypto related. And we have this thing, random math. But these, I don't think these are the same kinds of opcodes, are they? P4 instruction. Wait, how does whole words keep getting highlighted? Variant for random math.h is the thing we're including. We have kryptonite R JIT. Let's see. I don't know if this is something Monero specific. Minimalistic JIT code generator with random math sequence in kryptonite R. What is kryptonite R? Mining calculator? It's some proof of work thing. Kryptonite R hashing power for mining. And maybe it seems to be cryptocurrency related. And I don't know if it's necessarily specific only to Monero or if it's used by other things. We're in crypto. We see things like Blake and Cha-Cha. We might see Salsa, stuff we've seen before in, like, for example, Libsodium. Skein. I forget what it is, but I've seen it before. We are out of time. I've seen no opcodes. So do we have a stack? And let's look up Monero opcodes. Maybe it doesn't have opcodes. Once people realize what's happening, please watch this and understand why the hell Monero will be the most important asset in the what? In the coming years. 4 years ago. At least put some of your net worth into XMR. George Gammon is a crackhead. I have no idea what any of this is. This seems to be some so there's like a long history of like semi-conspiratorial thinking that you sometimes see in the cryptocurrency space, and so it seems like that's possibly what's going on. I don't know that person or what they represent, but if the first post is calling them a crackhead, I'm guessing that's kind of what's going on. So I don't know. I don't see anything really about opcodes. It may be that Monero works fundamentally different. So does Monero have opcodes and a stack-based language like Bitcoin, or is it more fundamentally different? It does not have. So Gemini is saying no. Monero does not have opcodes and a stack-based language like Bitcoin. They take fundamentally different approaches for transaction scripting. Here's the breakdown. Monero does what? Relies on cryptographic primitives like ring signatures and confidential transactions to achieve privacy. Offers strong privacy for transaction amounts and sender-receiver identities, but lacks the flexibility of a Bitcoin script. Okay, so maybe what we want is like a transaction. We're out of time, by the way, but just to see if quickly we can see maybe CryptoNote. Is that the basic building block? CryptoNote. CryptoNote basic. Yeah, that's where I was. We have outputs. Let's try Monero CryptoNote. The original Monero protocol was based on CryptoNote, which uses ring signatures and one-time keys to hide the destination and origin of transactions. Recently, the technique of using a commitment scheme to hide the amount of transaction has been discussed and implemented by Bitcoin Core. Maybe I should just read the white paper. Did I read the white paper? Is this the original one? CryptoNote, the 2.0. This is maybe not the original, but it might be interesting enough. You know, how do I get the raw PDF? See if Wallbag will load that. Okay, so it seems to do something else. I'm not sure if they still use CryptoNote. It sounds like the original was based on CryptoNote, but maybe we've moved away from CryptoNote. It's attracted the cypherpunks. Yeah. The other thing I don't know is what's up with Zcash. I think I knew some of the Zcash people back when all of this was going down, but I haven't followed along. Okay, so whatever they're doing, I'm not sure. This is not the place to learn that because on this show, we go into the code base without really knowing anything. But I will look up how Monero works so that if it ever comes up again, if we ever see it again, I'll have more of a place to start from. I don't think they're planning to have opcodes. Yeah, cool. All right, so whatever they're doing, they have some way of sending transactions. And so how do they handle the double spend? So let's ask Gemini. So how does Monero prevent double spending? With a mechanism called key images. Here's how it works. One-time addresses. It uses one-time addresses for receiving funds, unlike Bitcoin addresses that can be reused. Each transaction in Monero generates a new address. Key image. When spending from a one-time address, a special value called the key image is calculated using the address's private key. This key image is unique to each address and transaction. Then we have transaction verification. Miners check if the key image has already been used on the blockchain. If it's new, not found, then the transaction is considered valid, not a double spend. If the key image is found already used, the transaction is rejected. Here's the trade-off: privacy and efficiency. Miners only need to verify the uniqueness of the key. However, it's important to note, while key images prevent simple double spending, there are ongoing discussions and research on potential vulnerabilities and advanced attack scenarios in the context of Monero's privacy features. I still don't think I really understand how. So one-time addresses. So each transaction has a new address. When spending from a one-time address, a special value. Okay. So I'm guessing it's only the destination that's new, because if you can spend from one and verify that it's spent from that address, it seems like that address has to exist somehow on the blockchain already. The key image is calculated from the address's private key. It's unique to each address. So I guess one of my question is, like, how do miners verify that the key image had any money to spend? Okay, so they don't. They only check if it's been used before. Monero uses another cryptographic technique called confidence transactions. This hides the actual amount being transferred in the transaction. There's some commitment scheme. Imagine a locked box. Al Gore would approve. It's an Al Gore. It's an Al Gore joke. Because we're very timely on the show. The miners can verify that the box hasn't been tampered with, but cannot see the amount inside. Okay. Yeah, I don't know. Do they use a UTXO model like Bitcoin? I'm not sure. If they use what is UTXO? Something unspent transaction output. Yeah. Okay. I'll ask. Does Gemini says no? I don't know. I guess I'll have to read the white paper. We have ring CT outputs, which can be seen as a loose analogy to UTXOs. However, these outputs don't directly expose the amount or the specific address that holds them, while Monero doesn't directly use. Okay, so I have a Monero wallet with 0. What's the Monero currency called? Is it XT something? XMR? With 0 XMR. I want to send 1 million XMR to my friend Joe. Where does this process fail? Or does it succeed? It failed at the very first step. Insufficient funds. You cannot send more Monero than you currently have in your wallet. In this case, the balance is so transaction sending typically involves steps like specifying the address, ensuring the amount you want to send, setting any transaction fees, signing the transaction with your private key. However, in step 2, the software will likely prevent you. No, I wrote my own Monero client that doesn't prevent me from sending from. Will likely. I'm trying to create a transaction with insufficient funds. It will likely occur at a later stage in the process, depending on how you implemented. It might be rejected by the network. When I attempt to broadcast it, full nodes validating the transaction will likely reject it due to insufficient funds. They use the ring commitment proof of ownership, but cannot fulfill the requirement of the spender having enough unspent outputs to cover the transaction amount. Yeah, so this somehow is the, I guess Gemini doesn't want to call it UTXO. That's fine, but and this is related, I think, to the thing we saw on the Bulletproof documentation page, that there is some verification that the sum of inputs and outputs, the difference of the inputs and outputs sums to 0. And that is how they, and so that's bound up in the proof. That I guess that would be part of the Bulletproof code if you wanted to find that. And I think to really understand how that works, you'd have to understand enough about the, like what exactly the crypto scheme they're using, like how are they using ring signatures, what are you signing, that sort of thing. But it seems to ultimately come down to something like an unspent transaction that you have to be able to point to in order to spend it. And that's enough of that. I'll leave that there. So that's Monero. The code looks cool. The crypto, I think, was cooler than the code. I wasn't so into the code style. It makes it a little bit hard to read. And if the code is hard to read, that does have privacy implications for something as privacy oriented as Monero. Code readability is important, even just so that, like, if you're you want to make sure, like, when you're doing code review, that it's clear to you what's happening. So I'm sure that the people who write and work on Monero day to day have a good sense of what's going on. But we saw recently, like, I think that what was it, CloudStrike? One of those big companies just had a major failure from what appears to be something like a null pointer. And if you're not going, if you're going to use a language like C++ or C, then one of the defenses, other than things like static analysis, making sure you're using smart pointers, those sorts of things, but one of the defenses is just having readable and clear code. And it wasn't bad. It's not bad at all. It's just like some of the, like, variable names are just like really short. It doesn't seem to be trying to optimize for readability in particular, as opposed to other things. But that's okay. That's not the end of the world. That's just my one real takeaway from the code point of view. Search for double spending. Okay, sure. How about I just search for double? We have double blah 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 blah. Do we have lots of these? Okay, so I can search for maybe double spend. Oh, double spend. Okay, crypto.h. And we have TX pool. And the ring signature thing. And hard forks, which we'll ignore. The daemon handler. There's some, just like an error message from the daemon handler. An error message from the RPC server. Some stuff in blockchain.h and TX pool. which is, I guess, mainly a double spend. If meta double spend seen, then do this. Transaction verification utils. This is maybe some translation file, although I think that's also the suffix for TypeScript. And then some blockchain stuff and a bunch of it. So that was a good idea. And we're way over time, but I'll do just a little quick jog through these. Not that window. Here's the highlighting. Okay. To spend money to a key, the sender. So where are we? Crypto.h. That's not where I would have expected the code to spend money, but here it is. To send money to a key, the sender generates an ephemeral key and includes it in transaction output. To spend the money, the receiver generates a key image from it. So the sender is generating an ephemeral key. I'm guessing like a regular old key. And the receiver is generating the key image. No. To spend the money, the receiver generates a key image from it. I guess we used to be the receiver and now we're spending it. So now we're the sender is maybe how to interpret that. Then he selects a bunch of outputs, including the one he spends, and uses them to generate a ring signature. Okay, so including the one he spends. So are the rest decoys of the outputs? So I had thought maybe that the ring signatures were used to hide who had sent the transaction, but I guess they're being used to hide which output the transaction is coming from. To check the signature, it is necessary to collect all the keys that were used to generate it. To detect double spends, it is necessary to check that each key image is used at most once. Okay, so that actually clarifies a little bit, assuming I'm understanding correctly now that the ring signatures, the set that can sign the signatures are the outputs, the things that have received money. And so this is just a header, and this is just generate key image, which is inlined, I guess, because we use it a lot, and void, and we give it a public key and a secret key, which is probably the same as the private key, a reference to a key image, and I guess we call crypto ops generate key image. Cool. What else can we find? This says, this is what, take tx, and we have a comment. It takes a transaction with the given hash from the pool. You give it the hash of the transaction, a return by reference. Okay, so this is some output parameter. The second one is going to return by reference the transaction taken. And I guess the rest are maybe returned, or at least a few of them are. We're also going to get the transaction as a blob. And the transaction's weight. The transaction fee. And some other stuff. It returns true unless the transaction cannot be found in the pool. And then there's something about whether we saw a double spend. Here's RCT SIGs. This is the ring CT signature stuff. And we have some size type. So NDS rows is 3 times the DS rows. I don't know what DS is, but I guess these are the non-double spendable rows. See, identity chains paper. This is, okay, so this seems to be, what year is this? From Butterkiss, butterkiss.com. So this is more recent than the Ring CT v2 thing. But it refers to some paper so that you can look up what's going on crypto-wise. And that has something to do with double spends. And I think that's basically about it. Attempt to insert the newly spent key into the container of keys spent this block. If this fails, the key was spent already in this block. Oh, okay. If it fails, the key is already spent in this block. Return false to flag that a double spend was detected. Okay, so we're going to try to insert the key. If whatever our second is, if it's populated, or the key MDB has the key image, then I think this is the thing that detects whatever MDB is, some database of thingamajiggies, maybe key images we've already seen. So if we've already seen this key image, then we say that there's a double spend. All right. Okay. That's Monero. And now we will move on to PyTorch. Oops.